welcome to Breadboarding. In the previous video we took our 8088 processor and all its supporting logic, the bus buffers, latches and address decoder, and we added an electrically erasable read-only memory and 2 RAM chips to give us up to 1 megabyte of RAM. And we also hooked it up to our strip board bus rails here. This is a 78-way 0.1 inch connector which connects all the lines across here, and we also produce some labels so we can tell which each of the pins was. So this is the Breadboard PC 8088 version 2, and in this video we're going to be looking at the LED display and keypad, and it's video 4 in the version 2 series. So in the earlier projects what I've done is I created the LED display and the keypad on stripboard and veroboard, but this was quite time consuming, and so I've been looking at a simpler way of doing things for this version 2 project. So this is where we left things in the previous video. So this is all the circuitry I was telling you about, the address decoder, read-only memory and the RAM, and in this video we're going to be adding the keypad and 7-segment display port, the necessary logic to drive the 7-segment display, and we have 8 7-segment displays up here plus the decimal point, and also to drive the NeoKey keypad, for which we're using 5 rows and 5 columns out of the keypad, and at some point we'll also add the reset and abort buttons which handle the non-maskable interrupt and the reset button line into the power supervisor and reset chip. So if you have a look at the original Nanocomp 6809 design, which this was based on, so this schematic comes from the Wireless World magazine from July 1981, which was the basis for the original Nanocomp 6809 project. And you can see here there were 6 7-segment displays here originally, but we've added another 2 because they're 4-way 7-segment displays. You can see down here that this was the parallel port. So the Motorola 6821 PIA, as it was known, peripheral interface adapter, had port A and a port B. Port A had internal pull-up resistors, so if there wasn't a value on the port tied to ground or tied to 5 volts, it would default to 5 volts. And port B was used to provide this decoder value, and you can see this is a 10-way binary coded decimal decoder, and this was able to sync up to about 80 milliamps on each of these outputs. So depending on the value going in here, one of the 10 outputs would go low, and that was either used to scan the keypad, in that if a key was pressed then it would cause the corresponding line to the port A to go low. And you'll see in a lot of the code that a lot of the values are inverted so that we get a 1 for a key press rather than a 0. And also the display was a little unusual in that when a particular output was enabled for one of the 7-segment displays, then by default all of the segments would be illuminated, and only if a 1 was output on port A, this would actually cause this Darlington driver to ground the pin and it would turn the segment off. So in fact, you needed to output a 1 to turn the display off. And so again, you'll quite often see that the output to the segments will in fact be complemented or inverted. We have pull-up resistors here, and these are the pull-up resistors that mean that the 7 segments are on by default. Now the reason for doing this is because we're using common cathode LED displays, and there aren't really any good chips out there for doing this decoding, or there certainly weren't at the time when the project was designed in 1981. So in fact, the way how this works is that the Nanocomp monitor in fact both scans a 7-segment display and will actually select an individual LED display, and then it will output the value for those segments on the port A. It will then pause for a period of time to allow the segment to be displayed, then it will move on to the next digit, output the value for that, do that a number of times, and then it will go off perhaps to poll the keypad or something like that. So the routine that actually outputs the display is actually done in software, and it basically just selects each of the individual segments in turn and then outputs the corresponding code for it. And when actually scanning the keypad, it will actually output the number range for the rows on the keypad and then actually listen on port A for a key to be pressed. Now, some differences in the way how the original keypad works and the NeoKey keypad works that I'll talk about in the next couple of minutes. So there's one thing we need to be aware of comparing this original design with the current one, in that the bit mapping for the 7-segment allocation was slightly different in the original Nanocomp article. And if you see here, this is from the 7-segment display datasheet that I'm using, and you'll see that the A, B, C, D, E and F are reversed here. So the E and F here are different from the E and F here, and that means basically we just need to make sure that we get this mapping right. And what I've also done in this version, I've added in the decimal point, so the top data bit is actually going to be used for the decimal point as well. And what we need to do is, when we're doing the label for the 7-segment display, so if we look at the data sheet for that, this is the data sheet for the 7-segment displays I'm using. You can see down the bottom here we've got the forward voltage here, so this helps us to work out what value of resistor we need. So we're using 220 ohm resistors here, which should give us about between 11 and 13 milliamps going through the display. You can see for the common cathode display what the pin outputs are. So this label has actually been done to accommodate that. And what we need to check, that originally the port A, pin 5 is going to E, port A6 is going to F, and now these are reversed. So we need port A5 going to F, port A6 going to E. So if we just have a look at the schematic to make sure we've got that the right way around. This is the section of the schematic with this on. And if we have a look down here at, so if you look at E going here, and that's to PA6, and F is going to PA5, which I believe is the right way around. So we should end up with the correct values here. If we were to find that our 2, 4, 5, 9 and D characters were not quite right, then it may very well be that we haven't taken this into account. And the other difference from the original Nanocomp is that the chips that we're using for this, so the 2803 Darlington driver, this actually has built into it the input resistors here to drive from a TTL output. If we compare it back to the original diagram, you'll notice that this had the resistors going from port A going into the Darlington driver, and these resistors are no longer needed because they're incorporated within the chip. And this is the Adafruit NeoKey 5x6 keypad that I'm using. So you can get these, I think in the UK I got this from iHut. And the key thing about this keypad is it includes sockets for cherry style keys. So these are little sockets that we'll have a look at in a minute in detail and datasheet. So you can just plug in standard cherry keys. There are 1 or 2 restrictions on the size of them. I don't think low profile ones works. The PCB can be snapped into desired size. So if you wanted a 4x4 or a 2x6 or something like that, you can snap it. Now I'm just going to be using the 5x5 for the moment. I'm leaving this last column here alone for the moment. I don't really want to snap it because I might want to use it for something else. The rows and columns are joined across the keys, so it actually includes the built-in wiring for rows going across here and columns coming down here, and some pins we need to solder on here, connect that. There are even addressable red, green, blue LEDs on each of these keys, so if we were to hook this up to a microcontroller, then we would actually be able to control the colours of each of the keys. However, we're not going to bother with that for the moment. The rows are scanned with a 5-volt high line. Now that's a little different from the original Nanocomp keypad where we were scanning the rows with a low 0 volt. And so that results in a few differences that we need to take into account. And the columns up this way will show 5 volts for a pressed key, otherwise it would be 0 volts. So some of that complementing or inverting that we need to do in the software won't be necessary for this because we get a 1 for a key press. Another key thing is there is a diode for each key, and this prevents, when you press multiple keys, it prevents multiple keys perhaps from showing up on the input port when we're scanning this. So the main changes we require over the Nanocomp keypad, the rows need to be scanned as 5 volts, not 0 volts. A key press is now 5 volts or high, not 0 volts. But the only thing we need to be aware of is that TTL inputs default to high or 5 volts for no input. So we are going to need to tie the input to the port A to ground via pull-down resistors, otherwise it will always show as high. So this is from the schematic diagram, so I'm referring to these in the terminology of the keypad rather than the original Nanocomp. So we've got rows 1 to 5, columns 1 to 6, and the keypad layout is really a lot simpler than the previous one. The mapping in the Nanocomp was a little complicated. This pretty much matches the physical layout, and all I've done here is identified for port B which are the keys on each row, and also for port A which are the keys on which column. And this is useful when you come to test things, we're making sure that things are hooked up properly. And this is the keypad display, and you'll see the only real difference between this and the original Nanocomp is that the reset and the abort key, which are the reset button and non-maskable interrupt, these have been replaced with the code segment and extra segment keys. Previously I'd used the C and the E keys for that, but since we had a couple of spare keys here, I've used that for that. And this matrix again is just useful when we're testing it, and when you want to work out what the key scan codes are, this will actually help to do that. So let's take a look at the schematic in detail. So I'm going to fit this underneath where we put the RAM and the EEPROM. It only really needs to be connected to the data bus and a few control signals. So the control signals we've got is the I/O port range for the 400 series, which I don't believe the PC really used. So I've dedicated the 400 range just for this LED keypad interface. We need to know about I/O write, A0 line, reset active low, and the data transmit receive can be used for the determining the direction of the data sending. Now we're using a 74LS646, so this is a sort of bi-directional buffer stroke latch. It's a bit like a combination between a 245 bi-directional buffer and two 574 latches. So it's quite a handy chip that we've used in things like the IDE controller and in the CGA card previously. So although we need two chips to replace the peripheral interface adapter, I think this is a lot simpler to use, and the programming is much simpler because we don't have to set up all port directions and whether ports are input and output and all that sort of stuff. This PLD here provides the control signals for the blocks and the direction for the 646, and also provides the load clock for when we're writing to port B. So port B here is also connected to the data bus over here. So this uses the D0 to D3 line, so this effectively provides the decoding for port B. And out of here we've got the 5 rows for addressing the keypad, and then it then outputs the P0 to P3 values to go to the BCD decoder. Now although we're actually only using 7 segments here, we actually need to have the extra line here, SP3, because when we don't want any of the segments to be displayed, we need to be able to select some of the higher range. And if we look at the data sheet for the 145, we can see that when we've got any of the 0 to 9 values, one of the outputs will always go low, will light a 7 segment digit. But when there's a value above, then an invalid number, then in fact all of them will be high. So it means that if we output something in the higher range, then none of the segments will be illuminated, and that'll just mean that we won't end up with any stray lighting up of segments when we don't want it to occur. This decoder just drives the 8 digits that we've got here. The pull-up resistor here is what provides the power to light the individual segments, and the Darlington driver here, which is driven by the port A outputs here. When one of these is high, it will in fact pull one of these pins to the ground until it will turn the segment off, as I talked about previously. The only other difference I've needed to make here is originally the port A on the peripheral interface adapter had internal pull-up resistors that would actually pull up any open inputs to 5 volts. But in fact, because the keypad here, we're sending a high or 5 volts down one of these, and then we're looking for where we've got a 1 coming back on a column. Now, we can't have the input port here default to high, otherwise we won't be able to pick up when a key's been pressed. So in fact, what I've done here, I've added a pull-down resistor, so the port A0 to 7 is pulled down to ground using 4.7K resistors. This should mean that when we're reading the keypad, if none of the keys have been pressed, we should read 0 volts, and only when the key is pressed will we see 5 volts. And then for the keypad itself, we just need to wire in the pins for the row 1 to 5 and the column 1 to 6. So I've wired up column 6, even though for the moment we're not using any of the column 6 keys, but we could use these at some point in future if we wanted to. So I'm just going to show you the rules for setting up the two PLDs here. This is the control one, so this is only using some of the inputs here, but this actually provides the control signals for the clocks and the direction and the output enable for this chip over here, and also provides the clock strobe, the load port B, so that port B will read the current data values on the data bus. I'll actually put those into registers in here, and then we'll use those registers to decide whether we output a 1 for the selected row 1 to 5, or whether we output the 0 to 7 values to select the current digit that we want. And when there's a value selected on here, the value coming out here will be in the 8 and higher range, and so none of the output here will be selected. This is the control logic PLD. So the inputs I've already covered already, and this is producing the clock output to load the D0 to D3 into the port B. It also provides the clock to load the D0 to D7 into port A. Defines a direction for port A and also the output enable. So the rules down here are relatively straightforward. So we're defining a lot of the logic as being negative logic, partly because we want things to be on the rising edges for the clocks. From a direction point of view, we're going to leave the direction primarily going from the CPU out to the port, unless we're reading the data on port 400. Output enable is only generally going to be enabled when the I/O port range is not enabled, or if we're reading data from there. And we've also got a reset condition in there such that the output is disabled during the reset period. Then the other decoders, similar to what we had in version 1 of the project. So this is taking the D0 to D3 and the load clock signal, and we're producing the row 1 to row 5 for the keypad selection, which will be active high, and the SP0 to SP3 for P0 to P3. Change the name because there was a conflict with the video digital analog converter. And the key thing here, we're defining the port B input as a field, so that allows us to refer to the values of the port B just from a value rather than the individual D0 to D3. So we're just assigning the values to the row 1 to row 5 based on the port value there. And you can see here, this is the mapping that we're using, either where the first 4 values are going to row 1 to row 5, and then from row 5 to row 12 is going to be mapped to Q0 to Q7. So this enables the digits in the 7-segment display. And when we're in row 1 to row 5, or when we're above that, then these are out of range, and so we'll be enabling the Q8 output. So this means that none of the 7-segment digits will be illuminated. And the table here defines the rules for mapping port B to the output given those criteria, and the CUPL, WinCUPL, does all that conversion in the logic rules. Now have a quick look at the test program for this as well. So I did cover this in the earlier video series. I'll include a link in the top right hand corner, and it will be in the description below as well. This is based on the original code from the Nanocomp monitor, which was updated to provide a test program. So I've updated the key codes here, are now the NeoKey keypad codes. We're now only using the I/O port 400 and 401. Previously we're using memory mapped access. Some simplifications, but all we're doing now is we're outputting Nanocomp first of all to the 7-segment display, and we call the display refresh to display that. Then we're getting a key to wait until we start the next test, and this is basically outputting the 0 to F using the right 7-segment routine, then the left 7-segment routine. So this is just making sure that the routines I've got here in the 8086 assembly language are correct. Then we clear the display, and now what this is doing is waiting for a key, calls the display refresh whilst we're doing it, and then when a key is pressed it just displays the key code. So this will allow us to test that our key mapping is right before we start to plug this in to the rest of the Nanocomp monitor. This is display refresh code. So what this does is takes the 7-segment display codes in the buffer here and actually refreshes the display. So it sets the port A value between the digit 0 to digit 7 and then outputs the value, waits for a period of time, then goes on to the next segment and then returns. So disk refresh is quite often called from the key scanning routines. So as it's waiting for a key, it will also refresh the display. Key codes here have now been updated, and the get key is now where we were complementing the data coming in from the keypad. We don't need that anymore because we get a 1 when a key is pressed. And there are some changes here I need to make because the AL register is to use the IO in and out instructions and also to allow for the NeoKey keypad. So once we've tested these, what we'll be able to do is to then update the code in the main Nanocomp monitor, and hopefully that will mean that we'll be able to get the monitor working fairly quickly. So what I'm going to do now is to lay out the breadboard, the chips on the breadboard and the 7-segment displays, and I'm going to wire that up. I will speed it up, doing all the wiring in, and then when we come back we'll look at connecting the new board up to the rest of the Nanocomp, and we'll also look at plugging in the keys to the keypad and wiring the keypad into the new board. So here we have the current board. What I'm probably going to do is to fit the new board here. So I've fitted the 7-segment displays, put all the chip labels on. We've got the pull-up resistors in here as well. I've run out of the 2-way breadboard buddies, so they're on order. Just got 2 in there for the moment. So what I'll do is I'll move the board around a bit so that the camera can have probably a better look at this, and we're just going to wire it up. Okay, so we're going to plug in the power rails first, so the ground and the 5 volt, and there's a few pull-ups that we need to do as well. In the power up there, we will need to put some decoupling capacitors as well. Now I plugged this in the wrong place. That ground line should have gone an extra hole above, so that's a mistake I made at this point in time. And when I was wiring in some of these 7-segment displays, the 1 or 2 of the holes were 1 hole along. So this is just doing the common cathode Q0 to Q7 lines here. Those 2 were underneath on the other side, the D4 pin down the bottom there. We're just plugging in the rest of the common cathode to the decoder up there. Now we're going to look at all of the 7-segment values, so the A, B, C, D, E, F, G, and the decimal point, and the corresponding outputs of the Darlington driver there. And I think I noticed that I'd already made a mistake there already. Perhaps should put the labels on the side of the LED displays, probably easier. So we're just wiring in all of the lower side there, and then the upper side. Some of those holes on the left hand side there were incorrect, needed to move them along a bit later, and just wiring that into the rest of the Darlington driver. Now we're going to wire the inputs to the Darlington driver, so that's going to port A 0 to 7, and the order of those is in the order of the A, B, C, D, E, F, G, so they're going to alternate a little bit when going up to the port there. You also notice that those 2 black wires just covered underneath there were also actually incorrect. I needed to correct those as well, so I didn't do a great job of plugging those in. We're just adding the P7 port A7 line for the decimal point there as well, because it didn't have a label on it. Now we're going to wire up the P0 to P3 outputs from the decoder that go into the BCD decoder, and also wire in the data D0 to D3 lines between the bus and the PLD there. Now we're going to wire in the control signals, so the load port B, the reset, the direction block AB. So just putting in the reset, the load B there, put in the direction and the block AB, and wiring the data lines back in there again. So now we're going to look at the keypad. So I've already put in most of the keys in here and attached it all. And you'll see here that you've got standard cherry key keys here with 2 pins, and there's a sort of a post in there to fit through the hole there. And on the back you can see there's the little socket, so you don't have to solder anything in, it just plugs in. And they do recommend putting a bit of glue on there just to keep them in, but I'll leave that for the moment. And the labels, I just got some of these sort of plastic labels from Amazon. The keyboard specific ones aren't great because they tend to have the shifted characters. Now I just wired in soldered in some right angled 0.1 inch connectors, and I then put in the columns from 1 up to 6, and then the rows from 1 down to 5. So we've got a 6-way connector and a 5-way connector there. So the 6-way one goes into port A, and the 5-way one goes into row 1 to 5 on the PLD. So now we're just going to take the protective film off of the 7-segment displays. It turned out to be quite difficult to actually take off, very firmly attached. Put those in. So a good tip is lens repair tape, auto car lens repair tape, rather than getting expensive bits of plastic for filters to put on the 7-segment display. If you use this sort of lens repair tape, it does a good job, makes the LED display much more visible, and is a lot cheaper. So now we're going to just plug in the main data bus coming in from our strip board bus rails over to the right hand side there, and then the control signals as well. And I did need to add the DTR signal into there as well a little bit later on when I changed the configuration. The DTR line was on the left of that connector there as well. So now we're going to need to program the EEPROM and the 2 PLDs. So the control PLD and the decoder. So I'll do the decoder first. So we go into Win2UPL, compile it first, successful. Then we'll do the decoder as well. Now we do need to ensure the decoder that compiler minimization needs to be enabled, or else we'll get too many terms, so we just enable that there, compile that. Now we're going to go into the XG Pro and use the T56 programmer, and we've got the first chip in there. It's the ATF16V8. Choose the JED file and program that with no lock bit so that we can read it. And then we'll put in the other chip. So this is the ATF22V10C. Just read that first to check it's in right. And we'll program that as well. So now this is the test program. We're just going to assemble that. Select the EEPROM, load in the binary file there. This is version 2 here. Just check the bottom and the top of the file matches the bytes that we expect, which it does. So we'll program that, and then we're going to fit the EEPROM into the 0 insertion force socket and put the 2 PLDs back into the board up there. So I've managed to get it working, but I had to do quite a bit of troubleshooting first, so I'm just going to summarize the key things here. So I had to update the control PLD rules quite a bit. Made a few mistakes, so the DIR2 pin was defined as DIR in the logic rules, and I didn't follow my own advice of checking the pin mapping in the doc file created during the compilation process. So that was fairly easy to fix. Also, the polarity for DIR was not quite right, to fix that. Then I also came across the problem that by using the IO write and the inverted IO write, so that was how we could tell there's an IO read in progress, then in fact I came across this issue on the next slide. can see here that when the chip enable for the I/O range, the port 400 range, and I/O write went low, because I was using a combination of these two signals, you can see here down here that the direction signal here was coming out with these sort of dips here, which wasn't right and was going to cause trouble. And then, so what I did, from changing condition to using the I/O write, I changed it to use DTR, and you'll notice that the DTR signal is wider than the I/O enable signal here, and so we don't end up with that particular problem there. And I also did some chip tests for this control PLD in XG Pro. So I tend to first of all define the rules in the spreadsheet, so you can see here all the pins and whether or not we're putting ones and zeros and expecting highs, lows, or don't care. And in XG Pro, this is the rules then set up in here. So all those tests ran cleanly, and the chip seems to be configured properly now. There's also a few mistakes that I've highlighted in the voiceover as I went through the speeded up building of the breadboards. So the black jumper wire for the Darlington driver was supposed to go to ground, and it went to 5 volts, which certainly caused a bit of confusion. That was fixed. Fortunately, it didn't do any damage. I also found that I managed to plug in the select BA line, control line for the 646 was connected to 5 volts, not to ground. So that meant it was only using the clocked latch values, not the pass-through values, which I was expecting. Also, as I mentioned during the voiceover, the left-hand LED display, the top row pins, I managed to put the jumper wires in one hole to the right. So once I'd moved those over, it was all okay. And then, so when I was doing the conversion, the swap AH with AL, because the I/O out and in commands only use the AL register, then I'd managed to miss one out. So this is the version 3 of the software. So I made 1 or 2 minor changes. I removed the CX register because I didn't really need it. Went back to the original, and you'll see here that the AL and AH here, so the version 3 is using the correct AL. What I was basically doing was inputting the key press value from the port there, and then I was comparing it against AH, which obviously was never going to work. So it just went round in a loop forever. So that was fixed. Then the most interesting one is the original design. I had 4.7K pull-down resistors on the input for the 646. Now, you normally use pull-up resistors for things, and they're normally a 4.7K resistor pulled up to 5 volts. And I use that in the design here. However, I've subsequently found out that the pull-down resistor generally needs to be a lower value. So going to the datasheet for the 74LS 646, it shows that the A and B inputs, which are the main sort of parallel port type inputs, have actually got a 15 kilo ohm resistor on the input here. And when you do some of the maths, then the typical pull-up value of 4.7K. So when I was reading the values from the keypad, I was getting 9.4 when it was actually 0.0 on the input on the B side. And because of this 15K here, you can work it out. You'll find out that this would give an input voltage of about 1.2 volts, and that's above the TTL low value. Generally 0.8 volts for maximum voltage for a TTL low. Now what I have done is I've fitted a 220 ohm resistor array in there because I didn't have any smaller values than 4.7K, and that is drawing a fair bit of current there, but it should be okay. The chip should be able to handle it, but I'm going to try and replace that with a higher value once I have the parts. And there were 2 useful links here. I've never really come across pull down resistor calculations, but there are 2 URL links there which were quite useful. The one here that basically is talking about this a reasonably long stack exchange thing. What it says is the input current for 74LS logic is, so 1K is a maximum pull down for this that still guarantees 400 millivolt noise immunity. So you need to make sure that the voltage that you're putting on for a low has a certain amount of noise immunity. So you don't want to have it up around 0.8 volts. You want it about 0.4 volts. And then this also linked to another article, which is a far more extensive article, all the calculations. And again, this sort of says really a pull down resistor value is generally going to be 1K. So that's something I have learnt during this experience. Pull down resistors need to be quite low values. So also had a look at the Darlington driver, and the input here is also connected to the input for port B that we saw, which had the 15K resistor pulling to 5 volts, and also the pull down resistor as well. So we've got here a total of 12.9K to ground through this 2803 Darlington driver. And now the TTL low input is normally 0.8 volts or below. So if the input is above that, then we'll get this erratic signals that we're seeing. So also looked at the extract of the 74LS 646 datasheet, and the low input voltage maximum is lower here. It's actually 0.6 volts. So it would appear that the 646 may be susceptible to the low input voltage being out of range, and it was picking up obviously stray high signals to show the values we were seeing. Even when we had 0 on the logic analyzer on the B side, it was still coming up with sort of 9.4 values when we read it on the data bus. So I'm going to try both 1K and probably 470 ohm resistor arrays when I get the parts, and hopefully that will work a bit better than the 220 ohms. 220 ohms is okay, but the current is quite high, so it's probably going to be better to go with one of these values when I have them. So now in a position to be able to test the keypad and display. It shouldn't take very long. And all I've done is I've updated the keypad here, and the keypad now has the key codes that we expect. Now you'll see that the key codes are actually relatively straightforward. So the first digit really here refers to the row, so we've got the 0 row, 1, 2, 3, 4, and then just the position across there. So we're just going to power this on and check the values that we're coming up on the display, and we'll check it off against this keypad layout. Okay, so here's the keypad all wired up. I've tidied up. I have unplugged some of the logic analyzers that I've been using on this, and I'll cover that in the next video. And here's the keypad decoder output, so I'm just going to be using that on the side to actually check off against here. What I'm going to do is to just press the power on. We would expect to see Nanocomp come up first of all. There we go, we have Nanocomp. Now, when I press a key, what it's going to do is to test out the left and right display routines that basically should show 0 to 7 and 8 up to F. And it's using the left and right versions of those. So it basically takes a byte with 2 hexadecimal digits and it converts that byte to display up here. So the next 2 steps are just really showing that the conversion routines take a binary number and display it in hexadecimal are working. So that's probably I think the left or right is the first one. So it's doing all of the numbers from 0 all the way up to F. And this is the alternate side. I can't remember which way around it is, left or right, which is first. So that's showing 0 to 7 and then 8 to F. So all that's showing is that the software that's being used to display the key code is actually working. And now after we press key now, each time we press a key, we should actually get the key code coming up. So we're really just going to check it off against this here. So load is 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. That matches up. That's good. I'm just going to do it for the rest of all of these. So we've gone through the whole lot and all the key codes are coming out. So that means that the software that we've got in our testing rig is good, and we can then apply those changes actually to the monitor. So what we're going to be doing in the next video is we've done the LED display and keypad, and this also was video 9 and video 10 in the original Breadboard PC series. So if you want to have a little more detailed look at the background to that, then there will be links for those in the description below. And in the next video, we'll be looking at updating the Nanocomp 8086 monitor and actually trying to see if we can use the new display and keypad to test and debug programs running on this breadboard computer. So I'm going to finish the video there. So if you don't want to miss out on future videos, then please hit subscribe. And if you can hit like as well, it just helps to make the videos available to more people. Thanks for watching.